learn together, pass together, grow together. Today we gonna more learn about in depth of TCP protocol, like TCP having a three-way handshake to build a connection, and also it is having a four-way handshake or four-way handshake to terminate the session. So let's start it. Suppose host A wants to start communicating with host B using TCP. Before they can send real data, a three-way handshake must be established first. Let's see how this process takes place. So first, a host A will send a SYN message, which is a TCP segment with SYN flag set to 1, and SYN is short of synchronization or synchronize. So first, host A will send a SYN message, which is a TCP segment with SYN flag, which is set to 1, and SYN is short of synchronize. So to indicate it wants to set up a connection with host B, this message includes a sequence number of tracking purpose. Uh, this sequence number can be any 32-bit number, ranged from 0 to 2 to the power 32. So we use X to represent it. Okay. After receiving SYN message from host A, host B replies with SYN ACK message, which is called synchronize / acknowledgement. Okay. This message includes a SYN sequence number and an ACK number. SYN sequence number, let's call it Y, is a random number and does not have any relationship with host A SYN sequence number. Okay. The SYN ACK message indicates host B accept the talk to host A. Like a SYN ACK message represent that host B wants to talk to host A and ask if host A still wants to talk to it as well via SYN part. Like host B ensure that host B wants to talk to host A, and if host A is still in the connection or wants to host B, then they can start communicate. So after host A receives the SYN ACK message from host B, it sends an ACK message, acknowledgement message with ACK number to host B, and this confirms that host A still wants to talk to host B. Okay. Now in this process, 3 messages need to be sent, so we often call it three-way handshake. Nice. Now you really understand TCP three-way handshake, right? Host A can start sending real traffic to host B after the three-way handshake process. TCP also does nearly the same thing when one end wants to terminate the connection with TCP four-way termination process. Now the second part, that how the TCP end the communication with their four-way handshake. Now learn about it. Suppose host A wants to end the connection to host B, so host A will send a fin message, which is short for finish. The purpose of fin message is to enable TCP to gracefully terminate an established connection. Host A then enters a state which is called SYN wait, where it waits for host B to confirm that host B sends all his data and he also wants to terminate the session. So host A continues to receive a TCP segments from host B and proceed the segment already in the queue. But host A will not send any additional data. Device B will confirm it has received the fin message with an ACK message. From this point, host B will no longer accept data from host A, and host B can continue sending data to host A. If host B does not have any more data to send, it will also terminate the connection by sending a fin message. Host A will then add that segment and terminate the connection. It's like when host A wants to communicate or sends data to host B, it will send all his data, and when he finished or out of the data, host A will send a fin message to host B and said that I have out of or my data is completed, now I want to end the session. Then host B send its all his data. So for that moment, host A will wait, which is called a fin wait. When host B send all his data to host A, then host B send that ACK message to host A that I have sent my all data, I have no data left. Okay, and then host B also send a fin message that I also want to finish the connection. Then after receive the fin message from host B to host A decide or said through ACK segment or ACK packet that okay, I also received our fin message and now we have to terminate, or we can terminate the session. So this is a process of four-way TCP handshake to end the communication. TCP requires to establish or terminate connection before and after exchanging real traffic, so it is called connection oriented protocol. Other than UDP does not support these features, so it is called connection less protocol. Okay, now we're gonna learn some more feature of TCP and UDP. So TCP features are multiplexing using port number, flow control using windowing or sliding window, and reliability, which is error detection and error recovery. So first we learn multiplexing using port number. Suppose you are using a laptop for a web browsing or email communicating and FTP uploading at the same time. All them require using TCP, while your laptop only has one IP address with one network card. So how your laptop knows which packet received from the internet are dedicated for which application? So above the question is solved with port numbers. So the answer is port number. Each application will use a different and available port number to communicate with outside world. For example, your laptop can choose port 5000 for web browsing and port 5001 for email communicating, or 5003 for FTP uploading. Okay, so notice that your laptop can choose any available source port, but it must use predefined destination ports for well-known services. Port numbers are defined in three ranges. First is a well-known port numbers, which is assigned to a key or a core service that systems offer. Second is registered port number, which is assigned to industry application and processes. For example, 1433 is assigned to Microsoft SQL Server process. And third one is dynamic port number, used as temporary port for specific communication, where our laptop can use this port for communication. Okay, so the range of well-known ports are 0 to 1023, and registered port numbers are from 1024 to 49151, which is approx of 49,000. And the dynamic port numbers range is 49,000 to 65,535. Okay, so multiplexing relies on a concept called socket. A socket consists of three things, which is one is IP address, a transfer protocol, and a port number. So suppose the IP address on our laptop is 10123.1.1.1 and use TCP to access web server with port number 5000 or 50,000. We may write the socket like the IP address, which is 123.1.1.1, then comma TCP, then comma 50,000, which is the port number. For web server application running on the web server with IP 2000.1.1.1, the socket should be 2000, which is the IP address, then comma TCP, then comma port number 80, which is a usual or a well-known port for HTTP connection, as the web server uses this well-known port 80 for HTTP. The socket on each computer is unique, so the connection between two sockets on two computers identify a unique connection between them. Therefore, you can use multiple applications on the same computer at the same time. Each application will use a unique source port, or they cannot interfere with each other. we only mentioned about source port, but notice TCP requires the both source port and a destination port to build the communication. That means if our computer wants to connect to a web server, it must include the destination port in TCP header as well the destination port for web server. In the case it is 80 and the web server replies to our laptop, it uses the laptop source port as the destination port, which is 50,000. It's like TCP wants the source port and the destination port to build the connection. In our case, the web server has using a port number 80 and our laptop using a 50,000 port number for TCP connection. Okay, note the both TCP and UDP use multiplexing with port numbers for their services. Now the second feature, which is flow control using windowing or a sliding window concept. Okay. In this TCP header, there is a field called window which plays an important role in a TCP transmission. A window specifies the number of segments the sender can forward without receiving an acknowledgement. It is the key to transfer the data and flow control efficiently. Let's see how it works. After the TCP connection has been established, both the client and server use the window field to tell the other how many bytes of data it is willing to receive at once time before sending an acknowledgement to the sender. The larger the window size number, the greater amount of data that the host can transmit. For example, if a window size of 1 byte, so every 1 byte must be acknowledged before sending the next one. But waiting for acknowledgement after each segment would be very inefficient. So TCP tries to increase the window size to 3 byte or 4 byte, which means every 3 byte can be received before sending any acknowledgement from the receiver. Okay, as the bigger the window size, the fewer the acknowledgement needed to be sent and the more efficient the transmission is. So the receiver will try to increase the window size after each success transmission so that the sender can send more. But the window size cannot increase forever. TCP stops increasing the window size when the receiver does not send an acknowledgement or when the window size reaches its maximum value. If a congestion occurs on the link, then TCP may decrease the window size. In all, the whole process is mean that host A send a bunch of data aside, which is a limit by a window size, to the host B before not waiting for host B to acknowledge or send a packet of acknowledge of sending the next data. Like example, host A send packet 1, 2, 3 to host B, and after receiving the packet 1, 2, 3 by the host B send an acknowledgement packet of packet 4, which is mean it received the 1, 2, 3 and he wants packet number 4. Then host A send the packet 4, 5 and 6, which is bound by the size of windows. Okay, this is how the connection established. But if host B does not send the acknowledgement packet of the next packet he wants, so host A might think that host B didn't receive the packet 1, 2, 3. So it has to host A have to send the packet 1, 2, 3 again to host B. Okay, so this is the whole process of flow control using the windows or windowing or a sliding window. Now the third feature, which is reliability, which is error detection and error recovery. This is the most important feature of TCP. TCP must recover from data that is damaged, lost, duplicated during the transmission. But please grasp the difference between error detection and error recovery. First, error detection means the detection of error during the transmission. But error detection does not repair corrupted data, it just detects it. Okay? But on the other side, Error recovery means the detection of error and repair them. To achieve error detection, TCP adds some extra bits to the data, which is called checksum. A TCP sender computes the checksum value based on the contents of the TCP header and data fields. This 16-bit value will be compared with the value the receiver generates using the same computation. If the value match, the receiver can believe that segment arrived intact. If the value does not match, the receiver indicates an error occur and the segment is discarded, and a notification will be sent to the receiver depending on how the TCP stack is implemented on the receiver's operating system. To achieve error recovery, TCP uses the sequence number at the server side or a sender side, and acknowledgement field, which is at the receiver side in the TCP header. These two fields are also used to find out lost, duplicated segments and a damage. Okay.